Okay, now we get to a more realistic and more useful spline interpolation. We're not going to use linear splines anymore, but we'll use what's called a degree 2 spline or a quadratic spline. So a function q, this time q for quadratic, is a spline of degree 2 if the following three conditions hold. And it might look a little bit similar to the first degree spline. Okay, the domain of the function q is a closed bounded interval from a to b. That's exactly the same. You get something new here. Makes it a little bit tougher. Q, the spline function, and its derivative are continuous on AB. So it's defined, obviously, and continuous on the whole interval. Remember what that means. That makes the curve smooth. And the third point, there are points, which we call knots. We talked about those earlier, such that, and we have the same partition of the points going from A to B, where T0 is A and Tn is B, and we got a whole bunch of points in increasing, an increasing sequence of numbers here. And Q is a polynomial of degree at most 2. It's a quadratic, or it could be a line, but it's usually going to be a quadratic on each subinterval. In practice, you will only see where it says degree at most 2. In practice, it's going to be degree 2, except maybe at the first or last segment. Okay, we're going to talk a little bit about the theory. So quadratic spline interpolation, given, how many would that be? That'd be n plus 1 data points. So we're going to have n different segments, quadratic segments. To conduct spline interpolation, this is just a graph of a couple of possible points. 0th, 1, 2, and then the last 2 points there. I guess I have a dot, dot, dot here. Well, what we have is, between here and here, we have something like a y equals, let me just write the right-hand side. Let me write ax squared plus bx plus c. That's the equation of this guy right here. Now, I'm going to need several of these. So I'm going to call this A1, B1, and C1. And then this one is going to be ax squared plus bx plus c. But I'm going to call it A2, B2, C2. And that's that one right there. And the last one, let's see, I'm using the forward one for the index, so it's going to be a nx squared plus b n x plus c n, the equation of that last quadratic. Well, this is a tougher situation. Remember how we talked about if you take 3 points that are not collinear, you can find one parabola that goes through them? Well, here we only have 2 points. So could we have potentially more than one quadratic? Turns out the answer is no, because the problem is when these 2 quadratics meet, at this point it's got to be smooth. So effectively the slope as you approach it from either direction, the limit is going to be the same. It's going to be the smooth, a smooth curve here, and here as well between these two, and so on. So that's the tough part. Okay, so we have one quadratic connecting each pair of points, consecutive data points. And how many data points do we have? We've got n plus 1, right? N plus 1 data points. We know that. So how many quadratic splines does that mean? Just the same number as in the degree 1 spline, the number of line segments is n. It would be 1, 2, all the way up to n for the quadratic splines. How many unknowns does each one have? A1, B1, C1. 3. So from this line, what can we deduce or imply for here? In quadratic spline, each one with 3 unknowns. So we have 3n unknowns. So how do we solve for 3n unknowns? I'll just put solve for 3n unknowns. Well, we need 3n linear equations. Not linear, yeah, we need 3n. We need 3n linear equations in order to solve for that. You know, from pre-calculus or linear algebra, if you have 3 equations and 3 unknowns, most of the time you can solve for it. I don't even want to say most of the time, but if you have 3 linearly independent equations with 3 unknowns, then you can solve, but you need an equation for every unknown. So that's what our goal is going to be. We're going to figure out what the 3 times n equations are that we need to solve for. And we'll do that in the next video.